Now with this background of standard cell, now let's quickly look at the design process. This diagram we have seen earlier also. So it starts with specification, then we do synthesis, then the circuit in form of gate is generated, and in parallel we also do verification. Okay, so and this iteration step would be there, that if the verification is not complete, then or circuit is not correct, then we'll again go and change the specification. Okay, so the specification language could be a high level language like VHDL, Verilog, System Verilog, and verification is also done using some specific languages like Verilog we are using in our assignments for verification, but System Verilog and Spec E are also other languages which can be used for verification. Now if we have to design at for VLSI, which has large scale integration, which may have hundreds of thousands of transistors or millions or billions of transistors, then the only way we can design such a huge design is by divide and conquer, or by using abstraction, by using hierarchy. So the abstraction level detail, so we can start with algorithmic level or behavior level, then we have to go for register transfer level, and then register transfer level will go for a gate level, and then for each gate we can design a transistor which is coming from the standard cell library. So this design abstraction, as well as for designing a whole complete chip, the whole process, can also be represented using this Y chart, which is also called Gaski's Y chart. It represents three different domains of design. Behavior domain, where we are talking about functions, functionality or behavior of the application which we would like to generate an ASIC, and then we would like to convert them into gates, ALUs and their connections, etc. That's all called structural domain. And then finally a physical domain where layout is generated. So what is a layout? Basically a transistor will know that how many, where oxide has to be deposited, where gate has to be deposited, and where P and N concentrations would be there. So that is a transistor layout, and using the standard cell library we also will get to know what is the cell layout, layout of each gate, and then we can combine these layout of the gates to design our module layout, and then floor plan and the whole physical chip. So now when input specification is there, the input, or basically what we would like to design, is usually an application. Application essentially means it's a behavior, it's a functionality. So that functionality has to be converted into final structure in form of basic gates, and these gates could also be hierarchically combined into larger blocks like ALU or memory or multiplexers, etc. And these further could be combined into processors or accelerators, or a group of these, or maybe we can call them modules. So this behavior, going from behavior to structure, is called synthesis. So we have talked about it yesterday also, in the previous lecture also. In the previous lecture we have seen that the behavior, from after synthesis we will get a list of gates and how they are connected. This process is called synthesis. Now these gates could be further abstracted at different level of abstraction. They could be grouped together in form of like ALU or RAM or multiplexers or adders, etc. But there's still, finally we will have a gate level information. Now from the structure level also we would like to verify, so that's also a verification step which always go in parallel with the synthesis step. And yes, the next step so after this whole process of synthesis and verification, finally we will have all the list of gates and how they are connected. And when these gates are mapped to standard cell library elements, cells, then we also know that which gate will be mapped to which transistor, which particular cell. So we finally know the transistors involved associated with each gate, but it is still at the structural level. In the physical level, we will have layout information. So you remember when we say planar IC, so integrated circuit is all the transistors are in the same plane. So that means there is a physical location. In one plane, there is going to be a physical location for each of the transistors. So where all those transistors are laid out is called layout. So in the layout, we know where all the transistors are there, how they are connected to each other. So they would be connected using wires, but all that connection, that information is there. This whole information, that where transistors are there, how they are connected, is called physical synthesis. This whole process could be determined using physical synthesis. Now, what would be the steps? So basically, this is the replication of essentially previous lecture slide. So the first step is from the behavior to structure. So from behavior to structure, we can call it logic synthesis, or we can call it design synthesis. So in design synthesis, we can first step is behavior synthesis, where we are allocating tasks to multiple cycles and scheduling, designing finite state machine, allocating resources. And then the second step is logic optimization, logic synthesis. So here, from the behavior, we get to know what logic is there. That logic has to be optimized using two level and multiple level synthesis, multiple level optimization. So here I would again categorically say that although in the during the course we have focused more on two level synthesis, but eventually multiple level synthesis would be automatically the option. See, the number of in the cell library, standard cell library, we have seen the maximum number of input to a cell is a gate is 4. So if more number of inputs are there, automatically our two level circuit will also become multiple level circuit. So that is why multiple level combinational optimization for multiple level is more suitable. And for that, some sort of automation is required, because that problem is sort of NP complete. So that logic optimization would be there, and then after that we will also do FSM synthesis or sequential circuit synthesis. Finally, all of that circuit would be bound to standard cell library. So which means that for each of the logic, we will say that whether it will be mapped to 2 input AND gate or 3 input. So options are available every time. And further, we have to also see, based on the objective, whether the objective is low power, or whether the objective is high performance, or whether the objective is low area, minimizing the area. So we will see that various options of the cells are available for each functionality. So based on the objective, we can choose which options to be seen. So some of you have observed or have asked that now how we can limit. So given a clock cycle, how can we fit in more and more design into that? So here, if we take clock cycle as a constraint, then sometime we have to take high performance cells. The cells which would result in the lowest latency could be selected. So that's what would be in the purview of library cell binding, so that we can meet the objectives which are given as a design objective. Okay, so once this logical synthesis is done, that means we have the output of logic synthesis would be modules, their hierarchy, connections, standard cells of each module and their connections, and detailed layout of each cell is also there. So that means overall we can say the output of my logic synthesis is, I know the layout of each library cell, I also know how many of them are there, which of them are there, and how they are connected. So now I can take that as an input, and finally I can lay out, I can say the physical location of each and every cell and how they are connected. So that's what I would call detailed layout so this will become the output. So here not only the polygons for all the transistors, but also how they are connected. So each connection will also have their physical dimensions of the wire. Okay, that will all be included in the layout. So the steps usually followed in the physical layout are mostly can be categorized into 3 steps. One is floor planning, so that means overall dividing the area. So you can assume it like this, that if you are doing a city planning, then you would allocate some area, or maybe let's say campus planning, you would allocate some area to the playground, some area to the hostels, some area to the academic blocks, some area to the residences. And then each and every of this unit would be again further designed. You have to say that if it's a residences, then how many flats would be there, where all these flats should be there, how roads should be connected. So this is what is placement. And now placement is essentially who will live where. So you will have, let's say, 1000 students. These 1000 students, which room would be allocated to which particular person. So let's say we would like to optimize. We would say that each person should travel minimum. So that means you will say that the friends who are related to so all the friends should try to stay nearby. Okay, so this will give us the final placement where all the students who are related to each other, let's say one batch of the student who are all, let's say, in computer science or electrical, they would live together. So that would give them an option that they have to travel minimum. They will waste their minimum time in talking to each other, going to each other. So that's what is the overall placement objective, that the delay for each of the or number of wires would be minimum. And routing is essentially how the wires would be laid out. So given the connections in the cells, in the gates, how each of the wires. So the problem with the routing is that two wires cannot cross each other. So if there are two wires, they have to be at certain distance so that they do not short each other. The effect of one should not reach the other wire. So that's why routing become a sophisticated problem, particularly in the planar ICs. So once all of these things are done, then finally we will have a physical data of each and every layer, each and every metal layer or a transistor. Everything is that we can sum as a detailed layout. So once this detailed layout is there, then the next step will start, which is a fabrication process. So once the layout is there, then we have to fabricate the chip from the silicon. So this fabrication process is a very specialized process. It does not involve too much of understanding of digital design flow or even VLSI flow or about transistors. So you need not to know all of those things. So but what should be known is a separately different science. It tends towards the manufacturing process. In the manufacturing process, the layout is given, plan is given. Now after the plan is given, then you can go through the fabrication process. So that is why what most of the companies are doing today, they will design up till the layout, and after that only a couple of companies, 2-3 companies across the world, they are fabricating for all the VLSI related companies. So the idea was started by some of the companies like NVIDIA, Qualcomm, Broadcom. So they were the initial fabless or fabrication. They didn't have any fabrication facility. But today, most of the companies, even though they have their own fabrication facility, they are sending it to some common lab fabrication facilities so that the cost could be minimized. The common name which you can hear is TSMC, which is in Taiwan State Manufacturing Company. So UMC, SMIC is in China, Global Foundries in Europe. So these are the foundries which can take the fabrication data from anybody. Even you as an individual can go ahead and send to these companies, and then they can fabricate a chip to you. Okay. On the other hand, there are a couple of companies, they're still fabricating their own chips, so they have their own fabrication facilities like Intel, Samsung, Micron, ST Microelectronics, Infineon. There are many of these companies, they have their own fabrication facilities. But yes, since this whole fabrication process is hugely capital intensive, like hugely costly, as well as the whole fabrication process is also time consuming. Let's say you have designed something, it will take 6 to 12 weeks, so that your fabrication process is out, and then you can take the chip, so and then do the further processing. So this fabrication process, although an integrated part, but still an isolated way, because its input and output is clearly defined. Now once this whole fabrication is done, we have received the chip. The next thing is, before packaging, people will first test it, and they would have sophisticated testers. So because you see the technology is at the scale of 20 nanometer to 45 nanometer, the size of the pin, input output pin, would be very small. So before putting those pins, so the tester would try to give all those test patterns which you are usually giving in your Verilog as a test bench, so that tester will physically stimulate that 1.2 volt signal or 3.5 volt signal, whatever is the input requirement, and at the same interval whatever is required by the chip. So the testing is done, verification, this is also called validation and testing at this moment, and once it is verified that yes, now chip is correct, then people will will package, and once it is packaged, it will come in a ceramic board, or ceramic package, or a plastic package, or different kind of packages are there, so that they can minimize the heat. So and finally it would be placed onto a printed circuit board, so that it could connect to other such chips. So PCB designing would come even later, so once a chip is designed. So this is the overall process of ASIC design. So in today's lecture we have talked about different components of the ASIC design, and how, given a specification, how final chip is fabricated. So although we had talked about all of these things in quite brief, you can go ahead and do other courses if you want to know more details. So but at this stage also it's important to know that whatever you have learned so far, basically starting from gate design or a Verilog design, finally the whole process can be done. Even some, because of the free PDKs, you can and also their free EDA tools, using those tools you can also design your own circuit till the stage of physical synthesis and the physical layout. So all those details are there, and that can help you to go for a complete end-to-end chip design process. So with this we would like to conclude the course. This is almost So in the next part of this lecture we will talk about that what would be the future trends. So what kind of things you can study if you want to know more about digital design. Thank you very much.